Before we start, if you're enjoying these conversations, please make sure that you like or subscribe to Cleaning Up. It really helps other people to find us.
Cleaning Up is brought to you by Capricorn Investment Group, the Liebreich Foundation, and the Gilardini Foundation. Hello, I'm Michael Liebreich, and this is Cleaning Up. In the transition to a net zero economy, no sector is more challenging than aviation. It may currently be responsible for just 2% of emissions, but it has a far higher environmental footprint, and of course, it's growing very rapidly. My guest today is an expert on the technological approaches that we can pursue to get to net zero aviation. Rob Miller is Professor of Aerothermal Technology at the University of Cambridge and Director of the Whittle Laboratory, which is one of the world's leading jet engine research labs. Please join me in welcoming Professor Rob Miller to Cleaning Up. So, Professor Miller, Rob, welcome to Cleaning Up.
Thank you for having me, Michael.
Now, you've got a fantastic backdrop there. Nothing quite says genius professor like a whiteboard full of squiggles that nobody can understand. Where are you actually calling in from?
I'm calling in from the Whittle Laboratory at the University of Cambridge.
And let's take that as a starting point. Just tell us, what does the Whittle Lab do? Because you're the director of it, and maybe just, what was your route to get there?
So the Whittle Lab is really focused on the decarbonisation of air travel and land-based energy. So everything we do really is focused on accelerating that process. And my journey starts from a comprehensive in the northwest of England, in Crewe. I go up to Oxford University, study engineering, and the professor who's there has worked with Rolls-Royce. And I then go and work with him. He invites me to work over the summer to do a PhD with him, really working on Rolls-Royce problems. And that really generated my interest in working on problems on the boundary between academia and industry. And since then, I've moved to the Whittle Laboratory in Cambridge. I'm now the director of the lab and director of the Rolls-Royce Research Centre here. And I've spent about the last 30 years working on that boundary between industry and academia with companies like Rolls-Royce, Mitsubishi, Siemens, Dyson and Boeing.
This is the Rolls-Royce that does aero engines. Just in case anybody listening thinks that it's Rolls-Royce cars, this is aero engines and their land-based equivalents, and now branching out into other propulsion systems that to do with decarbonisation, correct?
Yeah, that's correct. It's all to do with flight.
And you're being quite modest about the Whittle Lab and saying, we worry about this and we do that, and your own background. I mean, this is one of the world's preeminent, what would you call it, aerothermal, jet engine, turbine technology centres, correct?
Yes, it's one of the leading laboratories in that field of aerothermal technology, a field where the aerodynamics and the thermodynamics, the thermodynamics when you boil a kettle and the properties of the fluid changes, where those two meet. And it's one of the world-leading labs in that field.
Tell us how many times you've all won the annual prize and who built the first turbine, just the short version of the history. Where did it all start and how many times have you won the big prize?
So it all started with Frank Whittle, who actually as a mature student actually founded Powerjets while he was studying as an undergraduate at Cambridge. And Powerjets was the company that ran the first jet engine in 1937. And many of those original Cambridge engineers that went with him to the company started to realise in the late 60s that the jet age was coming. And they set up the Whittle Laboratory at Cambridge. And since then, we've worked with these industries, really focused on supplying the technologies, hundreds of technologies, into the industry and into flying aircraft. And the laboratory, to give you some idea of size, it brings in just under 10% of the University of Cambridge's industrial income. And it's won the top annual prize for a piece of technical work in the field, the American Society of Mechanical Engineers Gas Turbine Award, 10 of the last 16 years.
Let me just give the background, if I might, Rob, of how you and I met. Because I've been doing a lot of work on hydrogen and, trying to communicate, among other things, just how difficult of a gas, just how difficult its physics are. And a lot of people don't realize that a cubic meter of hydrogen only weighs 71 kilos. And so a lot of people, when they say, oh, hydrogen is a fantastic fuel because it's so energy dense, of course it is gravimetrically, but not volumetrically. So to make the point, I've been saying, well, for aviation, for a long haul aircraft, it just won't work. If you look at the volume of the fuel that would be required, if it's hydrogen, to replace Jet A in a 747, it would be so big that the plane would be full of nothing else. And I've got this kind of pastiche photo of a plane that I've been showing. And you saw that on Twitter and you corrected me. And you came in and you said that I'm missing something. And have you got the tweet there that you actually sent?
I can't remember the exact wording, but it was something along the lines of it. Have you got it?
Rob, I've got it. And it says, I agree with most points, but the volume limit of aircraft is not fundamental like weight limit. You are falling into the trap most people fall into of retrofitting Jet A aircraft. And of course, I was most offended because I don't fall into traps. I'm the great Michael Liebreich and so on. But then I looked at your bio and I thought, maybe I shouldn't disagree with this guy. This could be high risk. And things kind of escalated from there. And you very kindly reached out and had me come and visit the Whittle Lab, and as a Cambridge engineer, more thermodynamics than fluids and so on, hugely impressed. Now, that point, though, about the long-haul aircraft and how you build it if it's going to fly on hydrogen, I was persuaded. What is the answer?
Well, the trap that people fall into that I alluded to in the message was that when we design a kerosene aircraft, we set the volume to be optimal for a kerosene aircraft. And so if you take the liquid fuel, which normally in an aircraft, the kerosene sits in the wings, if you take that off and you put it in as liquid hydrogen in storage vessels inside tanks, inside the fuselage, not only by moving to the fuselage, you push passengers out, but because the volume is 4 times bigger, you push a lot of passengers out. And that means either you limit the range and you are right, or you the energy used to fly one passenger 1 kilometer goes right up and it becomes uneconomic. But the trap people fall into is this idea of retrofitting. Now, if you redesign the aircraft from scratch, what you find is when you move the tanks inside the aircraft, the weight of the tank and the hydrogen is still around half that of Jet A, of kerosene. So you have an advantage automatically from weight. The fuselage of the aircraft obviously grows in size, and that increases the weight and increases the drag. But because of the weight of the hydrogen is lower, it means that the weight at takeoff of the plane is lower, and therefore the size of the wings goes down and the size of the engines go down. And so the drag and the weight of those components drop.
Because I was always thinking that you could get enough hydrogen onto the plane, but you'd need to go to a flying wing, which changes, every control surface, every component, every airport, and therefore we're not going to see that in my lifetime, your or my lifetime. But what you're saying is, no, you can do it. It still kind of looks like a normal aeroplane. It's just it might have a very long fuselage and it might have shorter, stubbier wings. I mean, sort of somewhere between what we think of as an aeroplane and a cruise missile kind of. It's got shorter wings, smaller engines, and it's much longer. But it still is fundamentally the same architecture, and therefore it can use a lot of common components and certification and the airports and so on. So it can be done.
Yeah, that's right. And in fact, we haven't built one of these, so there's an uncertainty in the weight. And we think that these sort of aircrafts will be within plus or minus 20% of the fuel burn per passenger kilometre of current aircraft. But one of the other interesting points is that as the range goes up, because the percentage of the aircraft weight that is fuel goes up, and because the hydrogen and the hydrogen tanks are lighter than the kerosene, actually the advantage goes up with range. So actually, hydrogen has an advantage at flying long-range flights rather than short-range flights.
It's completely counterintuitive. I was thinking that, it could do short haul, but long haul, forget it. Actually, it gets better. And another way of looking at this is so much of that 200 tons of kerosene, of Jet A, in a conventional aircraft is actually taking off itself. It's actually flying itself around. And so that's why you just don't need to do that. If you go to a much lighter fuel, then you've got a sort of much easier problem in some ways to solve.
Yeah, it's a sort of tankering effect. If you fly very long haul, a lot of the energy for flight is actually carrying the fuel for the latter parts of the flight. And that problem slowly reduces as you go longer range with hydrogen.
Now, I came up to the Whittle Lab, and it's an amazing experience. And I regret that we're not doing this live so we could go around and look at all the things you're doing. But what was interesting was that my next question was, well, does that mean that you think that all long haul is going to go to hydrogen? To which the answer was, paraphrasing, but no, because it's so, and in fact, the showstopper is getting liquid hydrogen to airports.
Well, I'm not sure it's a showstopper, but the very difficult thing. This is not a fundamental limit. If you look at the energy required, the jet fuel required at Heathrow, and you replace that 100% with liquid hydrogen, you'd have to bring in 60 liquid hydrogen tankers per hour into Heathrow. So it's an incredibly large number. Having said that, that's only half the number of HGVs that drive into Heathrow at the moment. On the other side of the problem, if you decided to pipe it in and liquefy it on site, then you're looking at probably 2 gigawatts to replace all the fuel in hydrogen, all the fuel at the moment with hydrogen. And that's sort of about 4 SMR reactors on site, and you can't imagine that happening. So I'm not saying it's impossible, but there's some big engineering challenges in doing it.
So we had the last episode, but one, was Tom Sampson of Rolls-Royce SMR, and their 470 megawatts electric SMRs, nuclear, small modular nuclear reactors. If you went to really the ones that are 100 megawatts, then you're talking about 20 of them. But the problem you've also got then is what are you going to do with the heat that you're rejecting? Because you're going to put that in the Thames. You end up raising the temperature of the Thames by some ungodly amount.
Yeah, I think the heat use of that, I think you could probably find other uses than raising the Thames. But your point about the complexity of that process is right. The difficulty here is there are no easy solutions. So if you decided to instead make electrofuel, so in other words, if you decided that you were going to take renewable electricity and you were going to do electrolysis of water to get hydrogen, and then instead of using that hydrogen directly, you were going to use direct air capture to get carbon dioxide, and then the Fischer-Tropsch process to make the fuel. If you look at that route, then the scale of the problem is also huge. So buying those tankers, those 60 tankers an hour, if you wanted to buy all the tankers to transfer liquid hydrogen to Heathrow every day, that would cost you probably about £1 billion, £2 billion. To build those wind turbines and solar arrays to produce that fuel, that electro fuel to come into hydrogen, is about £100 billion. So it's about a factor of.
When you say electric fuel, this is if you are making essentially kerosene, but you're doing it through a hydrogen electric and then hydrogen route.
Yeah, that's right.
Now, what we're doing is we're diving into what's actually one of your programs that you described and that we talked about at the Whittle Lab, where you start looking at the trade-offs between different solutions. But I think before we get into that, what are the other programs, right? We'll come back to how we solve decarbonized aviation, but you don't just do aviation, you also do some ground-based power, there's some turbines, you're looking at electrification. There's a few programs that you've got going on. Can you just give us a kind of an oversight Because then there's this one which is modeling all of those different trade-offs.
Yeah, so about 2/3 of the lab is on aviation, about a third of it's on land-based power. And the land-based power does things like hydrogen gas turbines, heat pumps, direct air capture. The 2/3 of the work that's done on aviation is all aimed at accelerating the path to an aviation system with no climate impact. But it really has two parts to it. One of the parts to it is about these new technologies working on battery electric, hydrogen aircraft, and advanced propulsion systems that would really lower the fuel burn per passenger kilometre in the longer term. And another part of it is to do with supporting programs like UltraFan, which is Rolls-Royce's next generation of aircraft engine, which will reduce the energy per passenger kilometre by about 20 to 25%.
And UltraFan is kind of the linear, I'm not sure if that's the right word, but it's a linear development of jet engines. It's the next one. It's even better. It's even bigger. It's very clever, but it is essentially 20% improvement over what we're currently doing. Is that right? And then the other things you're talking about are some more of the breakthrough approaches.
That's right. It's a more linear approach. But what if you move across to hydrogen or you move across to sustainable aviation fuels, the energy requirement to making those fuels is so high that you need to reduce the fuel burn per passenger kilometre. And this next engine, the UltraFan, is a way of doing that. But you're right, it's in a more linear way. It's the sort of obvious next step rather than those breakthrough technologies.
So let's look at, if we can we dive into, you've got a bunch of stuff around, so on the breakthrough front, you've got electrification, hydrogen, or, other approaches. What's the situation with electrification? Because you've got programs working on that, and they clearly work at the kind of small scale end. I mean, we're seeing that. Obviously, very few fully certified planes, but there is a Pipistrel, there's a trainer, they're coming through. You've got people looking at planes going up to sort of 16 seats, 500 miles, those sorts of things they're talking about. What are the kind of physical limits? I'm assuming that's one of the things you're looking into.
Yeah, if you consider that we'll still be using lithium-ion batteries in 2050, then you reach a limit of probably about 600 kilometers for battery electric aircraft. You're probably talking in 2035 at about 400 kilometers operating range. So these are relatively short ranges. This is about 5% of the total aviation fuel burn. So
can I ask on that, is that at any size of aircraft, or does it become easier if they're bigger, or is it easier if they're smaller? And does that include the sort of, is that the maximum you could fly before you fall out of the sky, or is that a realistic, you could actually put a route network together and fly 400, 600 kilometer routes safely?
So that's with operating reserve range. That 400 going up to 600 is with your reserve. So that's a safe operation. And we're doing a lot of work at the moment on how you would run those networks. Is this a canals versus railways moment when the technology comes in and suddenly it opens up totally new routes or ways of traveling? But the impact on the total fuel burn will be relatively low in that process. One important thing, you asked about the size of the aircraft. Now, at the moment, people are talking about aircraft that are between about 6 and 9 seats. And some companies are talking about going up to maybe 19 seats. The thing about battery electric aircraft is they are range limited, but not size limited. And so you might see a move towards bus-sized aircraft if the business model drove them that way between major cities. You could fly London, Manchester, things like that.
So that might be a 60-seater or 120-seater, but it's going to have to do a very, very short run.
That's right. And it's very important to make sure that aircraft is powered off renewable electricity. And one of the major problems is that when you operate them, they are a business model. You use so many flights a day, then you have to fast charge them at very specific times. So they don't work particularly well with renewable resources. So you either have to run them off the grid, which makes them very polluting, or you have to have on-site battery storage that stores that renewable electricity and then allows you to use it at the time that you need to fast charge the aircraft.
I suppose with my background, I'm less worried about connecting it to the grid and so on, whether it is through a buffer battery or to connecting it to a high voltage grid. We're going to have to be investing so much in the grid that doesn't kind of scare me, on top of all of the transportation, all of the heat pumps, the electrification of industrial heat and so on that we're going to be doing. But clearly charging it is going to be a problem. And what about battery lifetime? Because you're presumably going to operate these batteries not just in the middle range of charging so they last forever, but you're going to be pushing them pretty hard, are you not?
That's absolutely right. It's very different than cars. So you are fast charging them and you're using them in repeated cycles every day. And at about 2,000 to 3,000 cycles, if you're really hammering them, you have to change the batteries. This very much depends on the actual aircraft. Some of the aircraft are not hammering the batteries as much as others. But it could mean that you're replacing the battery at the upper end every 2 to 3 months. And so the battery becomes like a fuel. And then you've got to really control the after use of those batteries or the recycling process. And on the upper end, the companies that are hammering the batteries the hardest and are not recycling the batteries in some way for some other purpose, the climate impact of those batteries is sort of getting up to the CO2 impact of the flight. It's not quite on the top end, but it is large.
Using batteries for 2 months and then discarding them, even full recycling is not cheap.
No, it's not cheap. It's not cheap at all. But the difficulty is that because the operating range of the aircraft is so limited, as soon as you get, say, a 20% drop in the energy density per unit weight, then you can't run your routes anymore. Whereas with cars, you don't mind that dropping over the lifetime of the car.
Is anybody looking at battery swapping for this use case?
So we have looked at battery swapping. It is problematic because one of the critical things about battery electric aircraft is the overall weight of the aircraft, like any aircraft. And so a lot of the companies are trying to sort of work at a systems level to optimize weight out of it. And if you want to have battery swapping systems, your weight will be higher. And it's the energy per unit weight of the whole aircraft that matters, not of the battery. And so that can drive you in the wrong direction.
So as soon as you start adding extra racks, extra access, extra structural strength in order to compensate for then you just lose any advantage.
That's right.
Now, electrochemistry is not your core thing, but you did say if we're still using lithium ion by 2050, what is your sense, because you must talk to these people a lot, that there might be a breakthrough solid state or something? Is there going to be a step change that changes that picture?
I mean, it's a very hard one to call. I mean, predicting the future in that way. I mean, if somebody gets a Nobel Prize in batteries, then it might accelerate it suddenly. But I don't see, having reviewed most of the battery technologies that are available, that any of them are close at the moment.
Okay, so that is short distance, and presumably at that point it kind of beats all the alternatives because it's simpler and so on. So I'm assuming, maybe you'll disagree, but I'm assuming that means all the short haul, all of the general aviation, a lot of working helicopters, tourism helicopters and so on, they're just going to go electric because that will work and that's kind of done. Is that fair? Can we move on?
That's right. That's right. The operating costs, the safety, they win at up to that 400, 600 kilometer range.
All right. And so now let's move up. What happens beyond that? Because there's, broadly speaking, there's two schools of thought, I guess. One is it's going to go hydrogen. Well, I suppose there's going to be all sustainable airline fuels, in other words, Jet A, but made in a different way that's zero carbon. And then there's another school of thought that says, no, it's all going to go hydrogen. And the third school, maybe we should frame it like this, that says, actually, it'll sort of segment, and there'll be some chunk that will go to hydrogen and some chunk that will go to jet sustainable airline fuel, Jet A equivalent.
Well, I think if you look at the longer range, maybe 1,500 kilometers, you could build, and you see with companies like ZeroAvia, fuel cell aircraft have really the potential to do those sort of ranges today. And the nice thing about hydrogen fuel cells is that because of the low temperatures, they don't produce nitrous oxides or soot. And there may be a potential, because of the low temperature of the exhaust of the engines, that you could do some sort of contrail management. And perhaps we'll talk about that later, that this cloud formation behind the plane that has a significant climate impact. So there are advantages of fuel cells. Now, fuel cells at the moment have the important parameter you should look at is not like batteries. It's not the energy per unit weight of batteries. It's the power per unit weight that limits them. They actually have a hydrogen tank on board that allows them to do more range. And the power per unit weight is about 1.5 kilowatts per kilogram, all packaged up with the extra stuff at the moment, which is about where internal combustion engines were in planes at the end of the Second World War. If you look at the Bristol Brabazon, the largest aircraft we've built in Britain, piston-engined aircraft, that's got a similar power density. Now, if you look at that power density and you put it into our sort of whole system modeling, you can fly 1,500 kilometers today at a fuel burn per passenger kilometer about 50% above jet fuel aircraft. However, there's a very non-linear effect occurs. And as you start to improve the aerodynamic technologies, you start to bring in new structural technologies, you find that the range rapidly scales and the fuel burn per passenger mile drops. And so we predict by about 2035, these aircraft will be going above 4,000 kilometers at a fuel burn per passenger kilometer only about 20% above a Jet A aircraft. So I think there's a real potential in that space.
What sort of speed would they be flying? Because there are some other limitations, like how quickly they can reject what heat they do need to reject, because unlike internal combustion or a turbine, there's no vast flow of air going through them and taking heat away that you don't want.
So that's one of the biggest problems. I mean, when Whittle invented the jet engine, one of the major advantages he thought was that it threw the heat out the back. The internal combustion engines had these big radiators, and the drag of those radiators and the weight is substantial. And with fuel cells, we're having to go back to that. So if you see a lot of the recent designs that are coming out of ZeroAvia and equivalent companies, they have these huge radiators that are sized on them using these micro tube heat exchangers that have been developed by reaction engines in the UK. But that's a key technology. It's a key technology unlock, the weight and drag of those heat exchangers.
And what speed, sorry, coming back to the question, what speed do you see these flying at?
Well, I think we're going to fly slower because it's more efficient to fly slower. But how that works within the business model and how the public will accept flying slower, it will be substantially slower. One of the key things in determining the speed of an aircraft is how many operations you can use that aircraft for a day. So there'll be a business case versus efficiency somewhere in that, but they will fly slow.
Okay, but even in that range, which if we're talking about the kind of 400 kilometers to 4,000 ultimately, you could still just use Jet A. You could just use a sustainable airline fuel made either as an e-fuel, an electrofuel as you called it, or a biological-based fuel, and you could just swap that out today and use the same airframes as we do, same aircraft as we do right now. So which is going to be cheaper?
Well, at the moment, if you buy, I mean, let me start by saying I don't like the term sustainable aviation fuel. I think it's a real PR stunt, an amazing PR stunt, because it contains within it two very different types of fuels. On one end, a biofuel, and on the other, an electrofuel made from renewable electricity. And the cost and complexity of those two are very different.
Sustainable airline fuel brought to you by the same people who brought to you natural gas, which of course is fossil gas. It's not natural at all. But there you go. It sounds marvelous. So sustainable airline fuel, we need to distinguish between those two types, right?
That's right. That's right. And on the first end, if you buy today a sustainable aviation fuel, a biofuel, it's made from used cooking oil, effectively. And the actual limit on the feedstock for that will mean that at maximum that can produce 5% of the world's aviation fuel. Now, if we move to other biofuels, we have about enough feedstock in the world to produce all of today's aviation fuel, but that's about it. And other sectors are going to need that feedstock.
When you say that, let's push. I mean, we're straying into the area of one of your big initiatives, which is this modelling activity, where you look at all of the different trade-offs. So we should just flag that this is a big area where you've got, serious programs running at the lab, and it's about these trade-offs between how much feedstock and what it might cost, but also the climate impacts. Correct?
Yeah, that's right. If you want to compare battery electric on one end, biofuels, electrofuels, hydrogen fuel cells, and hydrogen gas turbines, it's not just a technology problem. You've got to think of where the feedstock is coming from. You've got to think about the infrastructure you're building. You've got to think of human behavior, the economics and business of it, as well as the technology. And so we've set up what's called the Aviation Impact Accelerator to develop a whole system model, evidence-based model, which can strategically guide people who are developing policy and industrial strategy.
And so when you say the feedstock, if we go back to that question of the feedstock for now biological sustainable airline fuel, or whatever, I'm not sure quite what I should be calling it now. I'm getting it wrong. Yeah. Sorry?
A biofuel.
A biojet fuel.
Yeah.
Right. Now, when you talk about the feedstock, and there's enough to do aviation but nothing else, what feedstock are you considering? Because right now you've got this animal fats, but you've also got vegetable fats, but you've also got cellulosic ethanol that you could make and then translate into by an alcohol-to-jet process. So what feedstock were you counting in that?
Well, considering feedstock will depend where you are in the world. So if you're in America, it might well be different feedstock from if you're in Brazil. But the key thing to take away from this is that if you make a biofuel, then about 2/3 of the carbon ends up going up your chimney. And I think one of the best options is what we call PBTL, which is power and biomass to liquid. And this is a process by which whatever your feedstock is, you're taking all of those carbons as a source, and then you're doing the electrolysis of water to produce hydrogen, and you're putting those together with the Fischer-Tropsch process to produce your fuel. And in that way, you produce 3 times more fuel per unit of feedstock than you would with a direct biofuel route.
It's very interesting because I get a lot of people that say, well, because I point out how hard hydrogen is to use, and then they say, well, we'll just methanate it, or we'll just turn it into methanol, or we'll turn it into an electrofuel, an e-fuel. And I always come back and I say, well, where are you going to get the carbon from? And at that point, they quite often sort of disappear, or they start accusing me of, sort of taking money from EV charging companies or something silly. But it's a real challenge. Where do we get the carbon from? And yet in some of these pathways where we're making a biofuel, we're actually discarding carbon. In fact, even for biogas, when we use anaerobic digestion, we make some biogas and we stick that into the grid, but there's some CO2 which we separate off and we just lose it. I mean, it makes no sense, does it?
That's right. It makes no sense. And I think what we've realized from our whole system modeling is unless you've got a complex worldview of how much biomass of different sources from different parts of the world, where that's coming from, it's very easy to double or triple account and think you're getting out of the problem. So the next fuel you asked me about, was the electro fuel on this list. And the electro fuel is the one where you either take the biomass, as I said, as your source of carbon, or you take the direct air capture to get your carbon, and then you do electrolysis, Fischer-Tropsch to make your fuel. And that sounds very attractive because you keep the planes the same, the infrastructure the same. But the problem is that the cost of those fuels will be about 3 to 8 times the cost of Jet A pre-pandemic. And that's likely to double the price of your ticket. And more worryingly, the electricity required, for instance, to do one single transatlantic flight is about 1.3 times, 130% of a UK annual electricity bill. So it's an incredibly large amount of electricity required to make those fuels.
So this is, let's say, renewable electricity, though of course it could be nuclear, but this is then using that to electrolyze hydrogen, and then you need some carbon, and then you're going to combine those. So there's the processes of combining and turning that ultimately into something that's equivalent to, chemically equivalent to Jet A.
Yeah, that's right. So the Fischer-Tropsch process, you make a fuel, chemically equivalent. You have to distill it. You can only use part of it. And the other part you have to sell to someone else at the similar price of 3 to 8 times Jet A, which is problematic. And then you have this big problem that the energy requirement to do one single economy seat, one-way transatlantic, would be 130% of a UK household electricity bill. So the energy intensity requirement is incredibly high.
So, I mean, is this why you're going towards PBTL? So, did I get that right? PBTL?
Yes, PBTL. Yeah, one of the attractions of PBTL is that it doesn't require the uncertainty of direct air capture and the added cost of that process and the added electricity. So it's still energy intensive and it's still quite an expensive fuel to produce, but it's a sort of sweet spot in that it produces 3 times more fuel from your feedstock. So it's not as feedstock intense, and the technologies are there to do it today.
I think it's Hegelian philosophically. There's thesis, antithesis, synthesis. So thesis, we'll do it all from hydrogen. Antithesis is no, we'll do it all from biofuels. But synthesis is actually we'll do PBTL and we'll do a bit of each, and therefore get much more fuel. Do a bit of presumably there will be there'll be a hydrogen piece and a biofuels piece, but using all the carbon in the biofuels rather than just some of it.
So, I mean, that's right. It's probably the best fuel if you're feedstock limited, but hydrogen is still around half the energy requirement. So a lot of these solutions going further out towards 2050 are dependent on how much electricity you have available. If it's restricted, it's a real problem. And some of our modelling up to 2035 has shown this, that virtually anything you do in aviation pulls resources away from other sectors. And if you're limited in those resources, you can actually make the problem worse. And I think one of the things about government strategy is to invest in things that can be scaled past 2035 as we get more renewable electricity.
As we move land transportation to electric, that's going to free up a whole bunch of biofuels. Is that of the right order of magnitude, do you think? Is that going to help?
Well, in America, I mean, so there's a lot of pressure to go for using corn to produce biofuel. And it only works if you do a whole systems analysis, if you can capture the carbon that would normally go up the chimney in that process. And in fact, if you're interested in this, or any of the viewers are interested in this, they should. The Aviation Impact Accelerator has produced a tool called Recce, and this tool takes multiple fuel routes and it goes from the resources you put in, the water requirements, the land use requirements, the electricity requirements, all the way through to the full climate impact of the fuel. So in terms of the climate impact of building the wind turbines, of building the planes, of making the fuels, and then all the climate impact in flight, the nitrous oxide produced, the water vapor, the contrails. And if you look at that, you can see how those fuels are very different in their outcomes.
And we're going to put a link to that in the show notes, and I would encourage everybody to go off and have a play with that tool. There's all sorts of counterintuitive things that it shows, which is great fun and very much worthwhile, having a look at that. But you've used the word contrails, and that's one of the topics that I wanted to go on to, because the climate impact of flying, we're told, is only about half the CO2 in the fuel.
That's right. And when you talk about this subject, you have to be very careful, because you have to choose a time scale over which you're going to average, because the contrail only lasts part of a day, whereas the CO2 lasts hundreds of years. Now, if you take a 100-year average and you integrate up the climate impact, you find that the contrail has about the same impact on the climate as the CO2 itself. And the way that it does this is that some of the exhaust of the aircraft effectively forms persistent cloud. And that persistent cloud both traps in heat and reflects heat. And at certain times of day, certain parts of the world, one unbalances the other. And overall, we think it's a negative effect, and that the size of the effect is about the same as the CO2 effect.
Over 100 years, correct?
Yeah, over 100 years. And it's interesting, because that's 100 years of CO2 is equivalent to part of a day, that cloud formation. And it's even worse than that, because only about 5% of flights, 1 in 20 flights, produces a really bad persistent contrail. So that 1 in 20 flights could be, and the uncertainties on these are large, doing as much damage as the 100 years of CO2 of all the other flights.
It's quite extraordinary, because and if you're worried about, if you think we're going to be doing direct air capture in the second half of the century and getting it all back under control, so you worry about 2050, you worry about the temperatures in 2050, 60, 70, where you might say that there's some kind of a pinch point, then of course it's going to be even more than 100. The effect is going to be even worse. And it's all coming from one flight in 20.
Yeah, that's right. I think it's interesting, because say you shorten your timescale, say you're interested in about 2035, then obviously your timescale of which you're averaging the carbon dioxide goes down. And that 1 in 20 flights that produces the persistent contrail now is looking absolutely terrible. But there's an opportunity here, because changing altitude in the flight may well allow you, or we know, can stop the contrail forming. It increases fuel burn very fractionally, a very small amount, but it can stop the contrail forming. And this gives us a real opportunity for a short-term technology that could have a massive impact on the climate, reducing the climate impact of aviation.
So that would be just avoid those 1 in 20 flights that are really bad. That would be, you say, different altitude, presumably it's different weather conditions, different time of day, those sorts of things?
Well, so if you are, if you're moving freight, or you're the military, you have some flexibility over the time you take off. And so that may be something you wanted to play with. But if you're a passenger aircraft, you don't. But changing altitude does give you a chance to do it. The question is knowing when to change altitude. And there's a real problem here. And there's a wonderful analogy. So if you want to avoid getting wet when you leave the house on any day, you look at the weather forecast. And the weather forecast will tell you if there's a good probability of getting wet that day. But it won't tell you at any moment whether you'll get wet. And so to avoid that, you carry your umbrella with you and you put it up when you get wet. And a similar thing happens with contrails. It's very difficult to predict whether you're going to form contrails before you fly. And therefore, it's very difficult to avoid those contrails in flight. And you need some sort of added system that can tell you if you are producing the contrails and whether you change height. But there's great opportunity there.
Would that be on board the plane? So you'd have a sensor, you have a camera out the back going, okay, Mr. or Miss Pilot, we've got a problem here. We need to change altitude because it's forming. Or do you have some huge central system like air traffic control that says, right, you're in that corridor and you need to change the altitude?
Well, I mean, we're looking, I think in the field, we're looking for climate scientists and aviation engineers to really brainstorm about new ways. But there's a few possibilities. I mean, aircraft do avoid areas where there's turbulence at the moment. They communicate to each other. The problem is that the contrail forms quite a long way behind the aircraft. So the camera option is not easy to do. In busy corridors, planes may be able to see the contrails formed by other aircraft in the space, and that might be a possibility. Rapid satellite communication may well allow individual aircraft to see what they're doing. That is another possibility. But we're looking for methods. So one of your listeners might think of an interesting way of solving this problem. And by the way, just hot off the press, the American funding agency, ARPA-E, which looks at funding disruptive technologies, has just funded a program on clever systems for avoiding contrail formation.
Does a contrail ever reduce climate impact because it reflects so much heat away? Are there any good contrails?
Yeah, there are. I mean, there's two things to say about this. The first one is that we have to be very careful. You remember on Google Flights, there used to be a factor that was put on, a doubling factor on the CO2 effects to say what your non-CO2 effects. And one of the reasons they took this off was because it was misleading, because in certain parts of the world, there isn't contrail formation. And it tends to be in this North Atlantic corridor where it's particularly bad. So we have to think spatially around the world. And in some areas, it's not a problem. In some areas, it's a real problem. That we have to consider. The second thing we have to consider is the time of year. So if you take a morning flight in winter, I remember taking somebody on a flight. We've got this on the Aviation Impact Accelerator. We've got this sort of Google Flights of the future, and so we can take people on future flights and we can see the climate impact. And this particular person had just taken a flight from London to Berlin in early winter, took off in the morning, and we ran the flight, and the contrail was cooling on that flight at that time. So it was actually, that flight was making, but we must be careful when we talk about these things, because the CO2 effect is definite, but the contrail effect still has very large uncertainty bars. And as we move from kerosene to hydrogen, those uncertainty bars get even larger.
So I've got a few takeaways here. One is those North Atlantic corridor shopping trips to New York, which I don't do, are definitely bad. That we really ought to be paid carbon credits for certain flights because we're doing the good contrails and might actually be making things better. Those who are listening on a podcast will see that will not be able to see, but I'm actually smiling. But also there's a lot of uncertainty. It must be a very fertile area for research and for improvement, so that we can focus in on that 1 in 20 flights, which is really catastrophically bad. And that will actually reduce the scale of the problem, but it won't deal with the CO2 problem.
That's right. That's right. I mean, I think we're a long way from knowing how we can, as you were smiling, of incentivizing those good flights. But I think, I mean, we need a lot of work in that area, and it needs aerospace engineers to come together with climate scientists in a sort of warlike spirit of rapid technology development. I think we could do something relatively fast in this area if we could put our heads together.
Of course, there are people who would be saying, well, why is he smiling about getting carbon credits for flying at Sun? It's just geoengineering and we should be doing it. But I think we should probably leave that one, or we'll open up a whole can of worms. But you hosted 2 now visits of, I'm assuming at the time, Prince Charles, now King Charles. What did he tell you to do?
Well, that was very interesting because we realized about 10 years ago that the urgency of the crisis in aviation, and one of the big problems in aviation, the aviation sector, is the time it takes to develop new technology. It's about 10 years from an idea to the point where it can be considered an engine program. And so we'd worked for a number of years on cutting that cycle time down. And we'd improve the computational methods, the manufacture processes, the testing process, and we'd pulled that cycle down. And in formal trials with the government, we'd reduced the time from months or years to take an idea to demonstration to days or weeks, about a factor of 100. And this had been amazingly important for the companies we work with. And because of this, we are about to start work on a new Whittle Laboratory, which will contain the National Centre in Propulsion and Power. And the idea is to really embed these rapid technology processes into aerospace. And the Prince of Wales was coming down to open it. And before he came, we talked, and he said he didn't think we were thinking big enough about the process. He said he thought that we needed to think about the fuel production, how the airports worked, who invested in them, human behavior, biodiversity. And he said if he was coming, that we could organize a round table. And we assembled the first round table at Cambridge, and we had all the people around the table. And the second one we organized at Clarence House. And this was an amazing group of people. And it was quite shocking, actually, because we found that people just talked past each other. Because the aviation sector had been stable for 50 years, but people were talking a different language. And it was at that point that the Prince of Wales, and now the King, called on us to come together and build this global aviation model. And since then, we have 100 experts working on it all over Cambridge, MIT, Melbourne University, Rolls-Royce, Boeing, Etihad, MathsWorks, and all of these world experts are putting together this sort of world model that allows us to see how we can accelerate aviation quicker.
That model, that's the one that does all the trade-offs that you could possibly want to look at, and it looks at land use if you go with this fuel, and but you can really flex it in all sorts of interesting ways.
Yeah, we've done all sorts of things with it. We've got a sort of Google Flights model that allows you to sort of, as I've said, take a flight in the future, and it communicates to you in a level you understand, like the percentage of your household bill in electricity. We have another model, RECCE, the Resource and Climate Tool, which is designed to compare different fuels, and people can look at that on our website. And then we've also worked with the Department of Transport, and we've actually developed a tool for them, which allowed them to develop the UK Sustainable Aviation Fuel mandates. So it works at all different levels for different audiences. We take different parts of the tool, and we really think it's a way of sort of accelerating change in the sector.
Now, that tool lives in the cloud, but you are actually going to be digging and building. You break ground on a new actual physical lab.
Yes, we're going to build a new Whittle Laboratory, of which the National Centre will be part. We're breaking ground later this year. The centre is is really inspired in a similar way to Whittle's original team, who saw the jet age coming and wanted to build a laboratory that would produce the technologies that would underpin the jet age. And now we're building the new Whittle Laboratory, which will produce the technologies to accelerate the decarbonisation of aviation. And it contains both that rapid technology development is built through the building so that teams can come together, they can design technologies, build them, test them, and learn quickly. But it also brings together this holistic modelling capability so that people can see in this complex and rapidly changing sector which technologies to work on.
I want to finish by asking you a question I think I know the answer to, which is whether you are optimistic that we'll be able to solve the problem of decarbonised, and not just decarbonised, but decontrailized as well, aviation. Because in my view, aviation, the ability to fly around the world to different places, it's so important, culturally, socially, economically. I mean, it has given the world so much that if we can't do that, and we therefore, I assume, have to retreat from aviation, to me, that would be a huge tragedy, a human tragedy. It's the reverse of progress. So let me ask you that. Are you optimistic? Do you think that we are going to be able to crack this?
I think I am optimistic. We are going to have to fly less in the West. But pre-pandemic, only 11% of the world's population flew in 2018. And we can't deny the rising middle class in Asia, Africa, and South America the right to travel. And so even if we massively cut air travel in the West, overall air travel is going to grow in the world. And the sort of cultural good and good of communication that comes from that travel, I agree with you, we need to maintain. And I'm very positive that when we really put our mind to it, we can produce an aviation sector which has zero climate impact.
So it's going to grow, but we're going to use less of it in the West. I mean, would it be, I know that, how can I put it? We're going beyond engineering here, but do you think we need to be rationing flight, or do you think that we'll just let it cost what it costs? Being carbon negative will be more expensive, so we will naturally use less of it.
For me, the interesting thing about aviation is it's very unlike most other sectors in that it's what I call policy rich. So in the car sector, it takes incentivization to move to electric cars, but once you get to electric cars, they're cheaper than internal combustion engines, so they outcompete them. In aviation, there's going to have to be, in the steady state, a policy that makes people fly in these new ways, because jet A is always going to be more, always going to be cheaper as a way of flying. So governments need to think both about how they incentivize the right behavior, the transition of the right behavior, but how they make sure this process is fair, so that people in the rising middle classes across the world get a chance to take some flights.
Isn't this a huge problem, though, from a policy perspective? Because right now, the policymakers that are not climate specialists, they think that aviation is an unalloyed economic benefit, and they subsidize airports, and they refuse any taxation on airline fuel, and they will subsidize anybody who wants to come and make any components or any of the technologies, and the externalities are socialized. So we are miles away from the sort of policy-rich responses that you're talking about, aren't we?
We are miles away. I mean, this comes down to the king again and his insight at that moment when he met us. His insight was that this is the big whole system problem, and that the only way we're going to get the policymakers to make these brave choices is to give them, in a simple way, communicate the complexity of these systems and what the different levers do. And so we are running these workshops with government where they can work on the tools live. So they can look at the policy choices and then they can explore the consequences in many dimensions. And I think we have to look at new ways of developing policy and new ways of doing government, which can absorb this whole systems thinking. So that's another challenge, and that's one we're facing at the moment head on, the Aviation Impact Accelerator, and it's a very exciting one. In some ways, that is harder than the technology problem, but it's all part of the real problem.
Well, I want to thank you for spending time with us here today. Fascinating engineering, fascinating systems thinking. I love that it started with me being proven wrong. You know, I'm happy to say that doesn't happen often, but I really do enjoy it when it happens because I learn so much from that process. And I would very much like to continue to stay in touch, to hear about these programs as they develop, and perhaps to have you back on Cleaning Up periodically to report back on what will hopefully be your success in navigating this very complex space.
Well, thank you very much, Michael, for having me, and I would be very happy to come back. I have to say, your humans as a sort of as a whole find it very hard to shed ideas when they're proved wrong, and I thought it's a credit to you that you did so with such humility.
Rob, I'm glad you're so optimistic. Thank you so much for today, and I look forward to catching up with you in person soon.
Thank you.
So that was Rob Miller, Professor of Aerothermal Engineering at Cambridge University and Director of the Whittle Laboratories. Next week, we'll be sticking with the leading academics. My guest will be Professor Sir Chris Llewellyn-Smith, who is Emeritus Professor of Physics at Oxford, and he'll be talking about energy systems and power storage. Please join me at this time next week for a conversation with Professor Sir Chris Llewellyn-Smith.
Cleaning Up is brought to you by Capricorn Investment Group, the Liebreich Foundation, and the Gilardini Foundation.